Hello, everyone, and welcome to today's webinar, 4D STEM Orientation Mapping in Digital Micrograph with STEMx OIM. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. However, if we don't get to your question, we'll follow up later via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Fernando Castro is an application scientist at Gatan. He received his PhD in Materials Science and Engineering from Northwestern University in 2018 and has been working at Gatan ever since. Fernando currently supports imaging and diffraction products like STEMx and STEMx OIM and focuses on both customer training and new product development. Now over to Fernando.
Hi, everyone. Thanks so much for being here today. My name is Fernando Castro, as I was just introduced, and I'm really excited to be speaking with you all about our new product, STEMx OIM, which brings orientation mapping to 4D STEM data that you can acquire and analyze directly inside DigitalMicrograph with your Gatan hardware. So I'll provide an overview of STEMx OIM, have a couple of quick tips about collecting data for STEMx OIM, and we'll have room for questions at the end. So in case you're not familiar in general with STEMx, STEMx is our system that we use for collecting 4D STEM data in DigitalMicrograph, and it allows us to do a really wide variety of analysis techniques in DigitalMicrograph, such as virtual aperture imaging, differential phase contrast imaging, and strain mapping. Those were the original kind of features built into 4D STEM data analysis in DigitalMicrograph. And then in recent times, we've added also in situ 4D STEM data acquisition. And then in the latest release of DigitalMicrograph, which is version 3.62, which was just released a couple of weeks ago, we have the new abilities for doing custom scanning, for moving beyond just a raster scan with the DigiScan acquisition system, survey mapping, which is a form of a live virtual aperture and differential phase contrast imaging. And then, of course, what we're here to talk about today is diffraction pattern indexing and orientation mapping of your 4D STEM data directly within DigitalMicrograph with STEMx OIM. So there's a lot of different data analysis techniques that you can use on your 4D STEM data now within the STEMx system in general. Now, why are people interested in orientation mapping in electron microscopy in general? It's because you can look at the grain orientation and figure out the phase distribution of the materials you're looking at. You can do analyses like understanding grain boundary size and the distribution of the size of the grain boundaries, among many other things. And of course, the structure of the material relate to its properties. And so orientation mapping is a very powerful technique. Now, of course, I think many people who start doing orientation mapping do it in the SEM with electron backscatter diffraction analysis, or EBSD, which allows you to look at the Kikuchi patterns that are formed from electron diffraction, and you can index those patterns to figure out what the orientation and phases of a material. Now, that's a really good approach a lot of times for when you need a wide field of view of several hundred microns or micron level, for example. But if you need higher resolution and are looking at materials that have nanoscale grains of, say, 20 nanometers or less, or you need that degree of spatial resolution that's possible with the scanning transmission electron microscope, or STEM, compared to the STEM, then there's a huge advantage of being able to use 4D STEM data to generate these orientation maps, with the difference being that we are looking now at spot patterns primarily for the diffraction pattern indexing instead of Kikuchi patterns, and we have the much higher resolution capabilities of the STEM or TM, with, of course, some trade-off for the field of view that is possible in your analysis. And so when we do orientation mapping, we want to have data processing techniques that are straightforward, easy to use, and you can also correlate with other data techniques such as elemental analysis, which we'll talk about a little bit in this presentation. And so STEMx OIM came out of that essential challenge of wanting to be able to do high spatial resolution orientation and phase mapping of 4D STEM data. So STEMx OIM brings several advantages. One of which I think that we'll talk about first is the fact that you can do the automated orientation and phase mapping of your 4D STEM data without requiring any scripting at all. Everything is built into an easy to use workflow directly here within DigitalMicrograph. And so STEMx OIM takes your 4D STEM data and then applies a familiar kind of template matching algorithm that you may have seen in the literature or from in other places. And it uses that template matching algorithm built into DigitalMicrograph without the need for any scripting to set up the analysis, define any kind of templates, define any kind of crystal structure, parse through your data, etc. You work with the spectrum images of the 4D STEM data that you acquire directly within DigitalMicrograph, and you can get an orientation map out just like we see here of these cool nickel nanoplatelets. Something I'd like to point out very quickly is that here you can see some particles of nickel that didn't quite form into this nickel nanoplatelet type of shape, but we can still see them with the stem, and we can still index them with the stem as well. So it's a nice example of what's the spatial resolution that's possible through 4D STEM data analysis and orientation mapping with STEMx OIM. Of course, we can do more than just single phase orientation mapping. With STEMx OIM, we can analyze multi-phase materials relatively straightforwardly. This slide shows a really nice way of what the workflow would look like. So when you have either a single phase material or a multi-phase material, the way we do it is that we can feed a crystal structure into DigitalMicrograph, and you make a list of all the different possible phases and crystal structures that you want to try to do the orientation and phase analysis on. And when you have your 4D STEM data, for example, you'll get your diffraction pattern within the 4D STEM data, and DigitalMicrograph uses a template matching approach to find the best fit diffraction pattern at each pixel position. Now, if we were wanted to make sure, for example, what phase has it picked or investigate it in a manual kind of way, you have the ability here, which through what are called the heat maps in DigitalMicrograph, it essentially shows you the cross correlation result of the best fit or any experimental pattern with the simulated patterns that DigitalMicrograph can use, and shows you which ones are most likely with the brighter contrast here. So in this duplex steel, for example, we have this gamma phase and this alpha phase, and it's picked the alpha phase here, which highlighted by this blue circle here. But we can investigate all the different possible simulations and orientation space of either phase in a manual way to investigate our material in such a fashion. From there, we can automatically calculate orientation map, which we're showing here right in the middle, and then on the right-hand side, the phase map that's generated through the orientation mapping analysis. So it's quite a straightforward way of setting up a data analysis process for your 4D STEM data. Now, of course, when you do the orientation mapping, we want to also be able to analyze and assess the orientation analysis results with other bits of data. So, for example, here we have an orientation map of a gold film that was just deposited. So we see a very large distribution in the grain sizes and orientations that we see. And so when we do the orientation mapping, there's also other information that's given by DigitalMicrograph to the user for you to assess the results. One being the image quality map, which is a metric of how much diffraction information there is in the diffraction pattern at each pixel position in the orientation map, or sorry, in your 4D STEM data set. There's the confidence index map, which essentially is the cross correlation result of the simulated best fit simulated pattern with your experimental pattern at each pixel position. And then we have the similarity map here all the way on the right-hand side, which shows how similar or dissimilar pixels are to their nearest neighbor pixels. And it's a nice way of showing the grain structure really quite straightforwardly. So by understanding, for example, what the image quality metrics are, what the confidence index metrics are at each pixel position, and then looking at what the orientation result is, we can assess how good of a fit there was of the STEMx OIM results. directly within DigitalMicrograph. So the whole process is relatively straightforward, but there's a couple of things that are important to keep in mind about how we can acquire data in the best way for the orientation analysis. And one of those things is the convergence angle that we want to use in the microscope. And so here again, I'm looking at gold film, just like in the previous slide. Now we just have a larger grain size because it's been annealed somewhat. And essentially, we want to be able to look at spots in the diffraction pattern in our 40 STEM experiment. And that means that we want to, in general, use as low of a convergence angle as possible to get the best results. So for example, here in the middle, I'm using a convergence angle of 2.5 milliradians in Joule F200 that was used to acquire that data. And what that really means is that I was in mag mode and I was using the smallest condenser aperture that I have. And I can get orientation results in a lot of map areas, but in some areas we see here, the results here are green, which are not what we expect. And if we look at the pattern in those areas, we can kind of see why we're not getting the best kind of data that we want. We see the really bright transmitted beam, but then all the other spots that we want to try to use in indexing are really quite low signal to noise because the signal has been spread out over the entire disk area because of the convergence angle. So if we use a smaller convergence angle, in this case, what that meant is that I just switched from the mag mode to the micro diff mode on our Joule F200. We get now a 0.7 milliradian convergence angle. We see these much brighter spots with no other aspects of the experiment changed. And this gives a much better signal to noise to give much better indexing results. So when we go and want to do orientation analysis, that's one thing to look out for is what convergence angle we're using and trying to maximize the signal to noise at each spot as we do our analysis to get the best results. Something else that can be really useful in general for diffraction and 40 STEM, of course, is energy filtering. And energy filtering also can have a positive effect on the confidence indexing and the results of the orientation mapping. And so the data that these samples that I was showing of this gold are about 100 nanometers thick, which is not the thickest sample ever, but it's also not an exceedingly thin sample. And here's what a pattern looks like from a grain here with no energy filtering on the diffraction pattern. And then when we use a 10 EV energy filtering slit, we can see that there's a big reduction in the background signal on the pattern, and it improves the signal to noise in general of all the spots across the pattern there. And so one thing that I wanted to do is see how does this increase the confidence index. And so this map here essentially is the difference across many different grains of the analysis region in the confidence index, where the brighter grains here that we see in the image have a larger improvement in the confidence index metric with energy filtering. So we can see that the variation in improvement of confidence index does change based on what grain you're looking at and what the diffraction condition is for each of those grains. But there is, in general, across the entire sample, a improvement in the confidence index, with some grains having a very large improvement in the confidence index by just having energy filtering as well. So if you have a system that has an energy filtering, or an energy filter like the GIF Continuum, and you have a camera like the K3 or the Stello or the Continuum camera, simulator-based camera at the end of the GIF, you can get a really nice improvement in your results with the energy filtering there. And here's just what the orientation map here looked like of that sample there. And so those are two things that are worth keeping in mind as we go and want to try to collect some orientation data from our samples. Now, the other thing that we can do with STEMx OIM, because we're working within DigitalMicrograph, is do multimodal orientation analysis. So combining the structural information that we get from 40 STEM with complementary signals that we can acquire at the same time. So of course, we can do simultaneous EDS and 40 STEM data acquisition, since EDS is detecting X-rays and the 40 STEM is detecting the electrons from the microscope. And that's a really great and easy and powerful method for combining elemental information with the 4D STEM data. But what we can also do within DigitalMicrograph is sequentially acquire 4D STEM data and EELS data as well, as I'll show in a couple of slides, to have correlative 4D STEM and EELS data and have chemical analysis and also orientation analysis at the same time. And it's really cool. So here's another example of what the multimodal analysis can look like. What we have here on the left is a multi-layer film where the bright layers that we see here are gold, and then the dark layers that we see are amorphous silicon oxide. And so we can acquire simultaneous EDS and 4D STEM from this data set and do, for example, the EDS mapping to get our silicon, oxygen, and gold EDS maps. And then, for example, we can take this gold EDS map and use it as a mask to mask out the 4D STEM data and the orientation analysis results, so we see only the orientation information from our crystalline gold regions of interest. So that's one really basic way of how we can, for example, use EDS data to inform the orientation analysis that we're using and that we're doing by having these data sets acquired simultaneously and linked together automatically by the DigitalMicrograph, which is what we call eaSI technology. So that's EDS, but we can also do EELS. So what this slide is showing is an example of an analysis of these cobalt oxide particles done by my colleague Liam Spillane. And so what we acquired, for example, a bright field image of these two particles, or what we at least thought were just two particles of cobalt oxide here shown on the left. But when we did the 4D STEM data acquisition along with the EELS data, we first looked at the 4D STEM data and did the orientation mapping and found that there were a couple of different grains in the orientation map that were popping up here that we didn't quite see just through the virtual bright field image of these cobalt oxide particles. And so in these regions here, we saw three very distinct different diffraction patterns there. And so that made us look at then the EELS data a little more closely. And although we assumed we were just working with 2+ cobalt oxide, we can see by looking at the fine structure of both the oxygen K edge and the cobalt white lines that there are some quite notable differences in the fine structure of these EELS edges at these different regions of what we thought initially was just the same cobalt oxide particle. So by using DigitalMicrograph to sequentially acquire the EELS data and the 4D STEM data, you can have a really powerful method of combining, again, the diffraction information with the chemical and elemental information and result in deeper sample analysis capabilities that isn't really possible through other techniques or through other processing methods. So the last thing I just want to talk about also in terms of multimodal and correlative workflows is the idea that we can take our 4D STEM orientation analysis that we get within DigitalMicrograph and then put it into our EBSD workflows, because a lot of folks who are doing EBSD are interested now in 4D STEM, but want to still be able to do what they're used to, for example, using the STEMx OIM analysis software. So you can actually do that with STEMx OIM. We have a feature here that exports the orientation information to OIM analysis, and then you can open it up in OIM analysis and apply many different processing methods and display methods that are possible through the mature EDAX software. So for example, in this, again, another gold sample, there was all these different twin boundaries that we were seeing within the material. And so EDAX OIM has the ability to identify those twin boundaries and then remove the twin boundaries from the overall data set so that we can, for example, get a better idea of what the true grain size is and what the true texture is of the material here on the right-hand side with the twin boundaries removed. And if we look, for example, at the pole figures here, we can see that these three dark spots essentially represent the 60-degree orientation relationships in the texture that we were seeing from this 1-1-1 orientation that is found in the majority of the grains of what we were looking at in this sample. So that's a really cool way of also combining a 40 STEM data workflow with a EBSD data workflow in the SEM. Now, the last thing I think that's cool to talk about with STEMx OIM is the idea that we can leverage the tools that are required for doing orientation analysis and bring them to other areas of just diffraction experiments in the microscope. So because, for example, we need to be able to index a diffraction pattern to do the orientation analysis, we can also index diffraction patterns not just from an individual pixel in a 40 STEM data set, but we can index individual patterns that we acquire through TEM-based selected area electron diffraction patterns. So if you are just doing TM mode diffraction experiments and are always having the challenge of having to index your diffraction patterns and know exactly which spot is where, you can use the tools in STEMx OIM to help you. And these are two different examples of using STEMx OIM of indexing a single pattern. And of course, you can also do things like overlay the actual spot index on your patterns, which is super, super useful. Now, when you think of that idea and you extend it, you can actually then use the indexing to help guide an experiment, for example, to help tilt to a specific zone axis, right? So this is a very basic sort of proof of concept idea that I'm showing here, but we have essentially a silicon 110 sample that's tilted off the zone axis, and we want to tilt onto the zone axis. So we can, for example, look at a pattern here, use the STEMx OIM indexing, and then look at the heat map here, which shows us in this marker here approximately where we are in orientation space. And now as we tilt the sample, we can see that the marker is taking us further and further to the 110 type orientation, and we see the indexing here on your pattern. So it's a really cool way of using the indexing live in DigitalMicrograph to help you with more than just doing 40 STEM orientation analysis. And then when we also, coming back to 40 STEM analysis and orientation mapping, but also strain mapping in particular, something that people always ask about is how, what's the benefit of, for example, precession electron diffraction and using precession methods to acquire 40 STEM data. And so if you're not familiar with the idea of precession electron diffraction, there's a little schematic here on the left-hand side. And the idea is essentially is that you can use some method to apply a beam tilt and then rotate the beam at a tilt angle in a sort of conical fashion that allows you to get diffraction patterns that have a couple of things. One is that you'll have higher order diffraction spots in your diffraction pattern. The other is that you'll have a reduction in the dynamical scattering in the diffraction pattern. So you have more of a quasi-kinematical type of diffraction pattern and spots and contrast in the spots that you would expect. And those two things are really useful for orientation analysis, but also strain mapping if you do strain mapping in 4D STEM. And so what we're working on is developing a method for acquiring essentially a sequential tilting approach to acquire precession-assisted 4D STEM data in DigitalMicrograph using only software controls without the requirement for any additional hardware to be installed on the microscope to do this kind of analysis. And that works essentially because DigitalMicrograph allows, essentially has communication directly with the microscope for all the other stuff that DigitalMicrograph does, but it can do things like apply a beam tilt and then apply an image shift and a projector lens shift to keep things, for example, the scan image and also the diffraction pattern in alignment in the same place as a beam tilt is applied, which allows you to do a sequential tilting or precession-assisted data acquisition. So this schematic here is showing a quick example of how that workflow works. We can define, for example, a beam tilt and then how many numbers of tilts we want or steps in this kind of conical rotation fashion. Apply then that beam tilt and the required image shifts and projection shifts automatically to keep everything in alignment, and then acquire a 40 STEM spectrum image at all of the different beam tilt positions and then sum them together into a final output data set. And so the result here, for example, can be quite cool. On the top here, we have diffraction pattern of just silicon 110, as we were looking at the previous slide, without any precession applied. And then when you do a precession at, in this case, it was a 0.7 degree beam tilt precession, we can acquire a diffraction pattern like this, which shows us what we expect. We see diffractions, disks in this case, at much higher order or further out in reciprocal space. And then also, the contrast within the spots is more uniform compared to the diffraction pattern on the top. And so if we, for example, use that method to now go back to this gold sort of standard sample that we were looking at for assessing, the indexing and doing all of our development of STEMx OIM, we can see what's the effect of having the precession on the confidence index that we get. And so that's here 3 essentially different orientation maps that we're using. Here on the top left with no precession, in the middle with 5 different tilt positions or rotational intervals in our precession, and then on the right, 10 different rotational tilt intervals that we use. And so there's 2 things that we observe. One is that, for example, if we look at this grain that's highlighted by this yellow box, as we have more and more tilt intervals, we see that the orientation results give us essentially a more uniform result, and is something that kind of matches the diffraction contrast that we see here based off of this virtual dark field image of the area that we analyzed. But if we also look at the confidence index of that grain, we see that the confidence index improves significantly with only, for example, 5 tilt intervals at a 0.6 degree beam tilt. And then also you get even more improvement at 10 tilt intervals. But what's interesting to see on top of that is that you see a big jump essentially from no precession to a quick precession experiment essentially with only 5 tilt intervals. And then you see some kind of marginal return by going much further. And what that means is that essentially you can use sort of a quick precession kind of scan with the precession technique here to get a big jump in the confidence index and get improvements to the data quality relatively quickly. And so the confidence index here improvement that we were seeing was more than 15%, for example, in this grain that we're highlighting there. And so this feature that we're calling STEMx precession, for doing the precession data acquisition within DigitalMicrograph, is I think going to be quite useful for a lot of people. And right now it's currently under development, but we're starting to work with some people globally who are interested in it. So if you are interested, reach out to your local salesperson and they can get in touch with us and we can talk about that. So that in general was the capabilities of STEMx OIM and all the new things that we can do for orientation and phase mapping here directly within DigitalMicrograph. The thing I'll like to close on in general is just the idea that this is a new feature that was introduced in the newest release of DigitalMicrograph, which is version 3.62. And so STEMx OIM is one of those features, but I said at the start, there's 2 other features that were also introduced. One is the ability to do custom scanning. So you can move beyond a raster scan. For example, here we're showing a checkerboard scan. And there's been papers out there that show that by moving beyond a raster scan, we can mitigate some of the beam damage and sample heating and other beam effects on your sample to improve the data quality and reduce the damage rate in your material. So that's, I think, if you're working with beam sensitive materials, could be of interest to you. And if you have questions about that, again, reach out to your salesperson. And then the last thing is survey mapping, which is ability to do, for example, real-time live differential phase contrast imaging, as we're seeing here in this sample, but also virtual aperture imaging too. So we're constantly working on developing new features and analysis techniques for 4D STEM here at Gatan. And these are just some of the newest ones that we have been working on recently and just released. So with that, I'll wrap up my part of the webinar. Thank you so much for your attention and for joining. If you have any questions, type them in the chat. We'll get to a couple of questions right now. And if I don't get to your question today, you'll get an email response. We've also been recording this webinar, so it'll be available for you to rewatch it if you're interested within the next 7 business days, and it'll be available on the Gatan website. So with that, thanks again. And if you have questions, submit them in the questions pane.
Thanks, Fernando. We do have a few that came in so far. The first one, is it possible to demo the STEMx OIM software on my own data, and are there any software requirements?
Yeah, so the software requirement is that you need the newest version of DigitalMicrograph 3.62, as I was just saying. That's the #1 requirement. And then the other, it is possible to do a demo of the software. Reach out to your salesperson or fill out a sort of an inquiry form on the Gatan website, and we can get that ball rolling.
Okay. The next question is, does STEMx OIM work for multiple kinds of crystal structures more than just cubic?
Yeah, so you can use essentially any kind of crystal structure for the analysis. The way that that works, I sort of mentioned at the start of the presentation, is that you'll have a crystal structure that you essentially load into the DigitalMicrograph software. That crystal structure is typically a CIF file that you can get, for example, from the Open Crystallography database or some other database that you might have that you're using for EBSD analysis. And then also DigitalMicrograph with STEMx OIM comes also with a library of many, but not all, crystal structures and samples. That's a subset essentially of the structure library that comes from the EDAX EBSD software. So there's a lot of different places where you can get the structures that you need for the analysis. And yeah.
Okay. The next one is, how fast can data be captured when with STEMx precession?
How fast can data be captured? That's a good idea. So the STEMx precession, you should think of it as sort of a multi-pass 40-STEM experiment. So the speed of the acquisition for 40-STEM in general is limited by the speed of the camera that you are using and the frame rate of the camera. So the faster the camera you have, the faster you can acquire your 40-STEM data. And then that's the biggest sort of factor to consider. Then the other thing is, when you think of this as a sequential tilt approach, how many tilts you want to use. And that's why I was showing that you get a huge jump with, for example, only 5 tilts and a smaller increase in confidence index going to 10. So using the smaller, sort of faster, rougher acquisition conditions still gives you good results. That means you can acquire data pretty quickly too. And then just the third factor, as always, when you're doing a 40-STEM scan, is how large is the area that you want to acquire, and what's your step size. So in terms of how long it takes, it's variable, but those are all the 3, I think, biggest factors that will determine that.
Okay, great. Thanks, Fernando. I think that's probably all we're going to have time for questions for today. Anybody that submitted another question, we will get back to you via email. If you have any more, please continue to type them in the next minute or so, and we'll get back to you.
Thank you, everyone.